你们看到那个期中考的成绩，那 so if you have any question, go to Delta room 856 between 2 to 5 p.m. tomorrow, okay? And the teaching assistant will help you to resolve any question you have. So, well, usually the first midterm exam just give you a little bit feeling how we're going to evaluate your performance. And down the road, we still have second midterm exam and also final exam. And I mentioned to you that in the first day of the class, quiz is very important. Your performance in quiz is very important, okay? So we have multiple channels to evaluate your performance. If you cannot do well in one channel, you can still improve yourself through other channels. So if you get a good grade from your midterm exam, congratulations. If you cannot perform well in your midterm exam, that's okay. You can still improve yourself through the quiz, second midterm exam, homework problems, or final exam, okay? So don't be frustrated if you don't perform well. So on Monday, we finished our lecture with the capacitance, definition of capacitance. Well, basically, a capacitor is a device to store electric charges. So the simple physical meaning of this device is that it's a charge you can store per unit voltage. Okay, for example, you can store 1 coulomb per volt. Then this is a huge capacitor, very big capacitor. I hope that the next time the TA can carry a big capacitor to you to tell you how big the capacitor could be for high voltage equipment. 所以下回我们带一个那个先是那个大坑的capacitor 来给大家看一下。But usually, if you go to an electronic store, you're going to see those small capacitors for electronics, and there are different kinds of capacitors for storing the charge. And next time, as I promise you, that you will be assigned a homework problem to go to electronic store and search for those capacitors. Okay. Well, now that the definition of capacitance is charge per volt, so we ought to be able to calculate the charge on this device given a voltage. So I'm going to give you 3 examples in the next 3 slides and I'll tell you how to calculate the capacitance of a capacitor. Okay. The simplest capacitor could be just a parallel plate capacitor. A parallel plate capacitor consists of 2 plates, 上下2片金属板。然后呢, these 2 plates are connected to a voltage source. And once you connect this 2 plates to a voltage source, you can store electric charge inside. And given the voltage, there's a finite amount of charge, you can store it. So the purpose of this slide is to calculate the capacitance you can have from this piece of device. Okay, now we need to calculate the voltage across it and then deduce the charge on this electrodes. Well, assume that these 2 plates are very big, infinitely big. Well, it's an unrealistic approximation, but in this region, close to the center, is a good approximation for the electric field. So if you have very big parallel plate, parallel electrodes, let's ignore the fringe field. Okay, just assume that these two plates are very close to each other. 然后在这个中心的部分呢，它的场不受到外头这个断掉的影响。Okay, and we need to calculate the electric field everywhere, subject to some voltage across this plate. So let's first find the Gaussian surface. Okay, if we can find a Gaussian surface, then the problem becomes quite simple. And assume these two plates are infinitely long, infinitely big, and you have solved this problem before with a single plate. Okay, 那你可以看到 the upper plate, according to this configuration, you have some positive charges. The bottom plate, you have negative charges. So if you choose a Gaussian surface like this, you are going to enclose nothing because the total charge is 0. This device simply separates the two charges, negative charge and positive charge. So if you choose a Gaussian surface, on this Gaussian surface, you have from the symmetry, you have the electric field normal to this surface. But it turns out that there's no charge inside, so the electric field outside is going to be equal to 0. There won't be any field outside because from Gauss law, you have no charge. Okay. And in this configuration, you only need to calculate the electric flux density, electric flux on the top and bottom plate. Okay, because of the symmetry. 因为它是这个平面对称。好 ，Well, now if you choose this Gaussian surface, you prove that there's no electric field outside. Then you can now concentrate on calculating the electric field between these two plates. Okay, so now let's choose a different Gaussian surface. Okay, just choose this Gaussian surface right here. Okay, in fact, I should pull it down a little bit. I need to enclose it a little bit. Come down. Okay, now look at this Gaussian surface. Well, the electric field on top of this electrode has been proven to be equal to 0. So you don't need to do any integration for the electric field on the surface. But you have electric field right here. But you don't have to worry about the electric field across this surface and this surface because of the symmetry. 在一个这个无限大的这个平面的状况之下呢，你如果 argue 说你有个 electric field in this direction, I'm going to argue with you that because of symmetry, there must be an equal probability to have an electric field along this direction. So finally, we settle that there's no electric field normal to this surface. So you only need to calculate this surface. Okay. Now, suppose that you have a y direction along this direction. So the electric field is going to be, this is positive and this is negative, so it's going to along minus AY direction. And the surface area is equal to S. And this surface area is also point downward, so it's minus AY. And you're going to include this amount of charge Q inside this surface. Inside this volume, okay, primarily is going to be a surface charge. 有没有问题？所以呢 you write down a very simple equation to calculate the electric field as a function of the charge enclosed inside this surface. Okay, and this result is a little bit different from the result you have before. If you remember, you calculate the electric field associated with some surface charge density on an infinite plane, and this is not a piece of conductor. It's a sort of in your imagination there's a charge distribution, sheet charge distribution in space. And in this problem, you have to calculate electric field up and down. Okay, and it turns out that there's a factor 2 difference. Electric field along y direction, suppose this is y direction, it's going to be equal to rho s epsilon naught divided by 2. Because you have electric field along this direction. At the same time, you have electric field along this direction. But for this case, you only have electric field between these two electrodes. You don't have electric field outside. Okay, assume that you have an infinite electrode. Therefore, the fringe field is not going to come to this location. 了解了，这里有一个 factor 2的 difference. Okay, once you have this the electric field versus charge, then you have to continue to convert this into a voltage, because capacitance is defined to be the stored charge per voltage. Okay, so the voltage is the integration of the electric field over distance. 那在这个区域里头呢 the electric field is quite uniform. So the integration is very straightforward. This EY, if these two plates are very close to each other, then EY is not a function of Y. So this is very easy integration. You simply multiply this EY with distance to get your voltage. Okay, under assumption that these two plates are very close to each other, so there's no Y dependence on electric field. So this is sort of the equation we want to deduce the capacitance, right? This D is the distance between these two plates. So you just move this Q upstairs and V downstairs. You end up having a capacitance look like this. Okay, so this is how you calculate the capacitance. First of all, you express the electric field as a function of Q, and then integrate electric field to get voltage. And then you organize the equation so that the capacitance is equal to the stored charge per voltage. Okay, so you end up having this expression. But when you get an equation, you always have to think about what it means. Okay, well, it's proportional to the surface of this electrode. Well, this makes sense to you, right? Because if the surface is big, the amount of charge stored on this device is going to be big. So your capacitance will be big. So this is reasonable. But this D is inversely proportional to D. Think about this. If you have a small d, this means that these two plates are close to each other. So the electric field inside is going to be stronger given the voltage. So with a stronger electric field, definitely you are going to attract more charge. So small d give you a big C is also reasonable. Okay, now S over D is related to the geometry of the capacitor. And there's one parameter that is related to the material, which is epsilon. Epsilon, if you still remember, this epsilon is equal to 1 plus chi e, this electric susceptibility. This coefficient tells you how good you can separate charges in a piece of dielectric, right? So a big epsilon tells you that you can separate a lot of polarization charges in this dielectric material. 所以呢，大的这个 epsilon 告诉你说，哎，我这里可以有很多的这个 polarization charge， 所以呢，它可以储存很多的电荷在那个地方。All right, so this is this equation really makes sense to you. C proportional to the surface area, and inversely proportional to the separation of the electrode, and proportional to the permittivity. Okay, so whenever you get the equation, you want to understand it, but not just memorize the form of the equation. So this is the simplest form of a capacitor. And you can have a little bit more complicated form, having this kind of cylindrical symmetric capacitor. And this capacitor has two electrodes, one at the center and one outside, having a cylindrical shape. Okay, 所以正负极可以是这里跟这里。It really doesn't matter to a capacitor because by definition, capacitance is always positive. No matter how you calculate the voltage, that gives you a positive sign or negative sign, you always choose the positive sign associated with a positive charge. Okay. 所以在这个结构里头呢 you have done this calculation for the electric field on Monday in one of your quiz problems. Okay. 所以呢 again, you choose a Gaussian surface according to the symmetry. 它是一个这个圆柱对称的。So you pick up the Gaussian surface that is also cylindrical. Okay, and then according to this, you can deduce the electric field as a function of R in this region. Okay, you have done this calculation on Monday, so I'm not going to repeat it. So electric field as a function of R is going to look like this. And this Q is the amount of charge stored over a length of L. Okay, the total charge must be proportional to the length because the longer the capacitor, the more charge you can have. Okay, so it makes sense to you. So you get this result, and you have 1 over R dependence. Now you want to calculate the electric field. For this problem, it's a little bit different from the problem having the spherical symmetry, right? For the spherical symmetry system, you have ER equal to 4 pi epsilon naught R squared. And then this is the charge you have. So when you calculate the voltage, that is minus, you move it from infinite to a certain location R0, and then E dot dr. With this calculation, nothing is going to diverge, okay? Because you basically is going to have 4 pi epsilon naught R0 Q minus Q 4 pi epsilon infinite. So basically you take out this. So everything converges. But for this structure, we have an assumption that the cylinder extended to some infinite location. 在这里呢 if we want to have a perfect cylindrical symmetry, then this cable has to be extended to infinite location. So if you try to do this calculation, ER dot, say, also along R direction, dr, from, say, infinite to some location, then the calculation diverge, because the calculation of this become natural log 2 pi epsilon L Q. This is going to be a natural log 1 over R from infinite to R0. Okay, if we put this infinite into this calculation, you get something diverge. That is all because that this cable goes to infinite location, so you cannot do this. Okay, but fortunately, the voltage by definition is the work you have to do by taking a unit positive charge from one location to a second location. So let's do this. If you take this from R1 to R2, this calculation can be done you have a minus sign in front, the same thing, from R1 to R2. Okay, this calculation does not diverge. Okay, now you have a reference location at R1 instead of at infinite location. Okay, now you have some cable, and then your reference location is at R1, and then you simply take this charge to somewhere. This is R2. This is R1. Okay, so with this calculation, you have the result. Well, since you are calculating the voltage across from this electrode to this electrode, the radius of this electrode is A, the radius of this electrode is B, so you have a finite value for your voltage. And this is a good approximation because the cable can be very, very long, especially for transmission line. Last time I showed you the coaxial cable. The coaxial cable is very long, and the diameter compared to the length is small. So this is a good approximation. And then you have a voltage as a function of charge. So you can now calculate the capacitance equal to Q over V and end up having this. So again, this expression consists of two parts. One is related to the geometry, LBA. And the other one is related to the material. And again, this capacitance is proportional to the permittivity, because permittivity tells you how good you can polarize this piece of dielectric material. Okay, the stronger you can polarize the material, the more charge you can store in this device. So you have a capacitance proportional to the permittivity. Okay, and of course, the longer the coaxial cable, the more charge you can store. And then you have a natural downstairs. Okay, this is just a measure of how what the ratio of the radius B to A. Okay, if this B to A is small, if B to A is small, this means that this electrode is very close to this electrode, so you can have stronger electric field. Therefore, you have more charge. Therefore, you have a larger capacitor. Okay, so this is how you interpret this equation. 那在这个coaxial cable 这个经常用的一个用途，它很长，是用来传输一些微波的讯号。So what we care, in fact, is the capacitance per unit length. If you still remember, when we talk about transmission line, we define R, G, L, C. That is all normalized to per unit length. 每单位长度. Okay, so once you have the capacitance, then you calculate the capacitance per unit length by moving this length down to this expression, and then this becomes line charge density. That gives you this expression. So we start to make a connection between transmission line and the circuit element we calculated. Okay, 我们开始再把这个以前学的 transmission line 里头用到的电阻、电导、电容、电感，跟现在的这个场的这个计算连在一块。但是呢，这是在我们之前学这些 transmission line 的这个参数的时候，都是每单位长度。Okay, so this is a calculation for the capacitance for a coaxial cable. That is very important because we use coaxial cable in a lot of applications. A little bit unusual capacitor is like this. You have a ball. At the center, you have one electrode, a metal ball as one of the two electrodes. and then the second electrode is outside. Okay, between these two conducting materials, you fill it with some dielectric material with a permittivity of epsilon, and you are asked to calculate the capacitance of this capacitor. Okay, this is the less common, less popular than coaxial cable, but it's a good illustration as how you can calculate the capacitance with different geometry. Well, because this is frequency-symmetric, so now you can create a Gaussian surface to deduce the electric field. So this is quite typical to you, right? So just choose a Gaussian surface between these two conductors, and you end up having the expression that you are familiar with. 这个式子你很熟悉了 right? This is total charge you can enclose. Then this is the surface area divided by epsilon. OK， 那其实这个是刚开始从你的Gauss law 开始。Okay, you first find out D, then you find out electric field, and so you have to put the epsilon, the permittivity of the material, into this expression. Now you calculate the voltage, and that's something you are familiar with, right? Just put a minus sign here, and you integrate electric field over the radius from the first location to the second location, and then you have this expression. Well, so this is a very quick calculation because here you have charge, you have voltage. So just take a ratio of the charge over voltage, you get the capacitance you have. 所以这些计算很标准，你先算电场，再算电压，然后呢，因为电场是从电荷来的，所以你在算电场电压的时候呢，你很自然右手边会出现电荷。And then take a ratio Q over V, you end up having the result. And again, all the capacitance is going to be proportional to epsilon. That is the ability of the material that can be polarized. OK， 所以这些没问题。来，在这个电子电路里头，你经常要串接或者是并接一些电容。这个等效电容是什么？你以前可能高中的时候學過了，我們來看一下，或者普物的時候學過，再重新看一下它的這個計算。Suppose you have a serial capacitors like this, 1, 2, 3 up to n, n could be a large number. And the two ends of these serial capacitors are connected with a voltage V, and this serial capacitors can be reduced to an equivalent capacitor right here with a voltage V across it and charge positive Q and negative Q. OK， 这是串接的电容。那在这个里头呢，所有的这个整个电压是个别的这个电容的电压加起来。个别的电容的电压呢，都是等于它的这个电荷除以个别的电容。Because C is equal to Q over V, so you can write V equal to Q over C. Because everything is neutral here. So if you have a positive Q here, you have negative Q here, but this part is neutral, so you have a positive Q, the same amount of charge right here with different sign. 所以呢，你这里上面头所有的电荷都一样， so you have Q, 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 Q all the way to the end. All right, so the total voltage is going to be equal to V equal to Q divided by some effective capacitance according to this. So you end up having an expression for you to calculate the effective capacitance. For serial capacitors, the effective capacitance is equal to this expression, inverse of this expression. OK， 有点像并联电阻的计算，但是呢，它是串联的电容。So don't get confused, right? So this is the easy calculation. Well, if you have a parallel capacitors like this, 你现在有并联的电容，像这个样子 ，OK， and want to reduce this into an equivalent capacitance, CP. Well, in this configuration, the voltage across every capacitor is the same. Okay, it's the same because it's parallelly connected. So you have V here, you have V here, you have V here the same. But you store different amount of charge on this capacitor because for this is C1, C2, C3 could be different. So the total amount of charge Q stored in this system is the summation of the charge on individual capacitors. Q1 plus Q2 plus Q3. But Q, according to the definition of a capacitance, is equal to C multiplied with V. So this Q1 is equal to C1V, Q2 is equal to C2V. So when you make a summation, you end up having total capacitance, CP, equal to the summation of all the capacitance. Okay, so this is sort of similar to the summation of the serial resistance for 串联的这个电阻电路 ，OK， 所以这些都是something you are familiar with already long time ago. I just bring it up and sort of remind you. 有问题？串联的电容，并联的电容，它怎么计算？就是这样子。Okay. Now, energy is very important. As I mentioned to you, this world has a lot of trouble because people are competing energy. Energy is money, right? So you need to know how to calculate it. Now, if you have a charge in space, apparently there's energy in it because it's going to take some energy for you to assemble those charges. And in the next 2-3 pages, I'm going to tell you how to calculate electric energy associated with charge and then associated with field. Okay. 譬如说，你在空间里头有2个电荷。它里头储存了多少的能量在里头？你怎么想这个问题？哇，你要想说，就像这个地方有2个砖头，这2个砖头它储存多少能量？那能量是相对的。我们如果把砖头丢下去的话，你就可以知道它的确有能量，因为它会砸伤人 ，right？所以呢，你要算这2个砖头在这个2楼的地方有多少能量，那你就去把它搬上来花多少能量，你就是这2个砖头在这里储存的能量。Okay, so using the same concept, you can calculate the energy stored in this two charge system. Well, basically, everything starts from nothing. So if you have one charge somewhere in space, well, in somewhere in universe, we don't know, to start with one charge. Then if you want to put a second charge into the system, then you have to do some work to bring this charge from infinite to this location. So this is the energy stored inside the system. Well, because this problem is symmetric, you can also say that, well, somewhere in universe there's charge already there. And then I take this Q1 from somewhere at infinity and then to this location with a separation of R1, 2. So again, this is an easy calculation, right? Because this energy, you can easily calculate with the concept of the electric potential. The work require for you to take Q2 to a distance R12 from Q1 is this big. Q2 V2. OK， 这个 V 是 Q2 不在的时候，你算得出来的一个 potential. We call it V2. Be careful. When I say V2, it means 2 is not in the system. Okay, when I say V1, this means Q1 is not in the system. When we calculate the V, 当我们在这个系统里头 when we calculate V, we only consider this charge and then assume a unit positive charge somewhere far away. Okay, and then bring the unit positive charge to a location, a distance R from this charge. So the charge under consideration is this charge. So if I label this 1, this means that the second, I label this with 2, means that the second charge is not under consideration. Okay. And then if I want to move Q2 from infinite location to this R12, then you multiply Q2 with this V2. Well, the problem is symmetric about Q1 and Q2. Well, you can move the charge from infinity. You can move charge Q2 from infinity to R12. You can also have Q2 in this location to start with, and then you move Q1 from infinity to this location. Okay, and then you have this expression. It's not that these two expressions are the same. These two expressions are the same because you are talking about the energy stored in the same system. 这两个式子是比较一样，因为你只是在设计一个实验来算这个系统里头储存的能量，它是同一个系统，不管你实验怎么做，只要是正确的实验的话，whatever you calculate for the energy stored in the system has to be the same. Okay, so you can express this as Q1, Q2 V2, Q1 V1, or you can just do a summation and take 1/2 of it. Okay, 因为这两个是完全对称的一个两个完全对称的实验。Okay, so you can calculate the system energy by doing this. Well, this expression is going to be generalized into many particles. 这个是最简单的两个电荷的系统，有没有问题？我要从最简单的开始，所有的研究、所有的知识都是从最简单的建立。Now we add a third particle into this system. Okay, we add a third particle. Then we have to design experiment to calculate the energy inside. Well, the easiest is that you first assemble these two charges, and then try to bring in this Q3 to some location with the distance R13 from the Q1 and with the distance of R23 from Q2. So this could be the easiest experiment you'll do, right? And so you put these two charges together. You spend this amount of work, W2. And now you want to bring the third charge from infinity to some location. So you have to do a superposition of the electric potential associated with Q1 and Q2, right? 所以呢，你这里有一个 Q1 除以4派 epsilon 0 R13的这个 V 这个 associated with Q1， 这项没问题，没问题，哎。然后呢，你把这个电荷从无限远拿到这里来，你也必须针对这个 charge 的这个排斥力或吸力做点功，这个功的量就是这么大。Q3 multiplied with the electric potential associated with Q2. So the total potential, total electric potential seen by Q3, the total electric potential seen by Q3 is going to be from Q1 4 pi epsilon naught R 1 3 plus Q2 4 pi epsilon naught R2 3. This is the total electric potential seen by Q3. And don't forget the definition of our labeling. When we say V1, we're talking about the electric potential seen by Q1 for a system without only have all the rest of the charges. 当我们说这个 V1 的时候，在上一个系统里头，当我们说 V1 的时候呢，我们是在算这个 charge Q2 产生的 electric potential， right？ 当我们说 V1 的时候呢，我们是在算这个charge Q2 产生的 electric potential， 但是 Q1 不存在 ，OK， 在无限远的地方抓过来。同样的，这个呢是这个是 Q3 在无限远的地方要把它抓过来，所以这个呢我们把它叫做 V3。In this system, Q3 is the charge to be moved from infinity to a location R13 with respect to Q1 and R23 from the Q2. Okay, so the multiplication of this gives you Q3 V3. 所以在这个 labeling 上头的话，你要留意一下这里所谓的 V3 的话是 Q3 是那个从无限远移过来的这个电荷。那这个 V3 里头呢，式子里头只有 Q1 跟 Q2。OK， 当 Q3 还不存在的时候，这个 electric potential 是多少？算出来就是 V3。OK， 那again, the whole problem is symmetric for Q1, Q2, Q3. So we just did one experiment. This is Q1, Q2, and then you bring Q3 from infinity to a location. But you can do the same thing for Q1 and for Q2. You're going to end up having the same answer. Okay. 所以呢，你若做个实验做这个实验的话 now you have 3 charges like this. You can first assemble these 2 and then bring this from infinity to this location. And you end up having one expression. But the whole system, in fact, is symmetric. So I can first put these 2 charges here and bring this from infinity to this location. I can also calculate the energy stored in this system. Same thing, I can first put these 2 charges into the final position and bring this one from somewhere very, very, very far away to this location. These 3 experiments basically are the same and give you the same answer. 所以呢，在这个 what happened to OK， 所以在这里呢，你得到一个这个 W2 加上这个的结果，等于是这个部分呢，你之前已经算过是这个2个电荷的系统在那个地方 ，OK， 2个电荷系统在那个地方，那同样的。这是你算出来一组的这个实验结果，你可以做另外一组的实验结果 ，OK， 另外一组的实验结果。那这个另外一组的实验结果呢， 就是把其中3个的这个 charge 呢，用不同的这个 charge 抓到无限远的地方去，就是刚刚我给各位看的这个实验 ，OK。所以呢，这3组就最后得到结果会是一样。So let's take a look. Well, if I just do one experiment, then according to this expression, you can calculate the total energy. That is the double summation. Okay, that is double summation. If you just look at this expression, you have double summation in this so to summarize the form with n charges. But if we do 3 experiments, then we can in fact deduce another form that is equivalent to this. 所以我们开始做刚刚那个3个实验 ，OK。If we define V1 equal to the voltage taking charge Q1 from infinity to this location, it's going to see an electric potential of V1. OK， 那我们刚说有三个实验。第一个实验呢，譬如说这是 charge Q1，OK，charge Q1 拿过来，我所要做的功基本上就是 Q1 乘上这一项，然后呢，这是 Q2，if I take Q2 from infinite location to this location, then the work to be done is going to be V2 multiplied with Q2. And for this third charge, if I take this from infinity to this location, the work you have to do is going to be Q3 V3. 那这个式子呢，可以由Q1 V1 plus Q2 V2 plus Q3 V3 divided by 2 to get this result. OK， 你可以重新写下这个式子，用不同的实验的方法来写下来。OK， the good thing about this is that you only have one summation sign in your final form. That is easier. All right, you can write it down like this. You just do a summation of QK VK. And this apparently is simpler than this expression, although they are equivalent. You lump basically one of the summation sign into V. OK， 在 V 你把这个其中一个 summation 呢放到这个 V 里头来了，所以 you get a single summation. And this form, in fact, is a little bit simpler than this form in calculation, but conceptually is a little bit abstract, and you have to sort of go through this again by yourself and think about it. Okay, we'll continue from this point on next Monday.